In this video, we solve problem 9.2.12-T from Essentials of Statistics, 6th edition by Mario Triola. The problem statement says, listed in the data table are IQ scores for a random sample of subjects with medium lead levels in their blood. Also listed are statistics from a study done of IQ scores for a random sample of subjects with high lead levels. Assume that the two samples are independent, simple random samples selected from normally distributed populations. Do not assume that the population standard deviations are equal. Complete parts A and B below. It says click the icon to view the data table, of IQ scores. And we've got the IQ scores. Here's our list for that medium lead level. And then we've got summary statistics for the high lead level IQ scores. So if you want to, and I highly recommend that you do this, you can click this button here. You can open this data in StatCrunch or copy to a clipboard, or you can open it in Excel. I'm going to open it in Excel. I've actually already done that, and I've got that available for us when we need it. But you would just click here in order to do that. Okay, so part A says, use a 0.01 significance level to test the claim that the mean IQ scores for subjects with medium lead levels is higher than the mean for subjects with high lead levels. And then it asks, what are the null and alternative hypotheses? Assume that the first population consists of subjects with medium lead levels and the second population consists of subjects with high lead levels. So with that in mind, I'm going to share my paper with you, and then we'll talk through what the null and alternative hypotheses should be. Okay, so the first thing we need to do is identify the first and second population. Our first population is the subjects with medium lead levels. And the second population is the subjects with high lead levels. Now, with that in mind, we want to state our claim in terms of the sample means for these two samples. It says, test the claim that the mean IQ scores for subjects with medium lead levels, so that's the mean for this group, since they're population 1, that's mu sub 1, is higher than the mean for subjects with high lead levels. So they're saying that this mean is higher than this mean. That's our claim. Since it does not contain the condition of equality, it's just a strictly greater than sign. That's our alternative hypothesis as well. And to get the null hypothesis, we just change the sign from the alternative hypothesis to an equal sign. Okay, so this is what we're looking for on MyLab statistics. Okay, so the null is that they're equal, and the alternative is that mu sub 1 is greater than mu sub 2. Okay, so it looks like option D is our best bet. Great. And then it asks for the test statistic, and it asks us to round to 2 decimal places as needed. Now, in order to determine what test statistic is appropriate, we've got to go back to the problem statement. It says, assume that 2 samples are independent, simple random samples selected from normally distributed populations, and do not assume that the population standard deviations are equal. With that in mind, we're going to have to use the test statistic T. So I will use my paper to at least write down the formula and talk through what we're supposed to do and what we're going to do. And then we'll use Excel to do the calculations. Now, the formula for our test statistic T is x sub 1 bar minus x sub 2 bar minus mu sub 1 minus mu sub 2, and those are the values, or this is the value of mu sub 1 minus mu sub 2 assumed in the null hypothesis. And then we're dividing by this expression, which is an approximation of the standard deviation of a distribution of x sub 1 bar minus x sub 2 bar. Oops. Okay. Now, in order to interpret this, the way you want to think about this is you're starting with the distribution of x sub 1 bar minus x sub 2 bar. Now, it turns out that since x sub 1 bar and x sub 2 bar are normally distributed, And they are because they come from, or the samples were selected from normally distributed populations. The difference between those two is also normally distributed. And the mean value of that difference is actually the difference between the population means for those two populations. Now, when we are drawing this distribution, we are thinking about the actual value of x sub 1 bar minus x sub 2 bar we have for our two samples. If we compute those and then we take the difference, we want to know, is that value significantly high or significantly low given that the null hypothesis is true? So when I draw this distribution of x sub 1 bar minus x sub 2 bar, I'm assuming that the null is true, which means I'm assuming that mu sub 1 and mu sub 2 are equal to each other. Well, if they're equal, when I subtract them, I get 0. And then the question becomes, is the value of x sub 1 bar minus x sub 2 bar significantly high or low? The way we answer that question is we convert from this distribution to a distribution that looks very similar. It's going to be a student t distribution with the appropriate number of degrees of freedom. The student t distribution has a mean of 0, and the standard deviation is a little bit larger than 1. But we're going to find a test statistic t that corresponds to the value of x sub 1 bar minus x sub 2 bar that we have from our actual sample data. Now, we don't actually have these guys yet. So in order to use this formula, we're going to have to compute them. I believe x sub 2 bar and s sub 2 and n sub 2 were given to us. Those were the sample or the summary statistics from that group of IQ scores that we have for subjects with high lead levels in their blood. So we already have these three values, but x sub 1 bar, s sub 1, and n sub 1, those summary statistics will need to be computed from the sample data that they gave us. Because remember, they didn't actually give us the summary statistics for the medium lead group, but they gave us the original data set. So we'll have to compute those. Once we compute them, we can substitute them into this formula, and then we'll evaluate this expression in order to get the test statistic t. But again, the test statistic t is just a t value that corresponds to this x sub 1 bar minus x sub 2 bar. And we're trying to figure out, is that test statistic significantly high or low? Which is the same as asking, is x sub 1 bar minus x sub 2 bar significantly high or low? Okay, so let me just outline the plan. The next thing we need to do is compute x sub 1 bar, s sub 1, and n sub 1. We'll use Excel to do that. And then we'll compute all of these quantities. So we'll compute the numerator here. That's x sub 1 bar minus x sub 2 bar minus this. But this value here is the value that we get when we assume that the null hypothesis is true. So this will be 0. So this is our numerator. And then the denominator is this expression. If I call this A and I call this B, then this is going to be the square root of A plus B. And I'm calling those A and B because if they are called A and B, there's a formula in terms of A and B for the exact degrees of freedom that we're going to use later. Okay, and then once we've got this and this, we can divide them to get our test statistic. Okay, so that's the plan. Let's go to Excel and compute these summary statistics and then start computing all of this that we've listed here. Okay, so this is our data set for that first sample. So I will compute n and x sub 1 bar. That's the average for that group, the sample average or the sample mean. I know Mr. Triola would not like for me to use that word average. Excel likes the word average though. In order to compute N1, we just want the count of these values. I think you can see already that N1 is equal to 11 because we start in the first row and we go to the 11th row. But if it didn't happen to line up that way, and sometimes it doesn't, sometimes you're looking at a data or someone's spreadsheet and it doesn't start at 1, you can just type equals count and then select the cells that you're interested in, close parentheses, and you get that right, the correct count. So there are 11 values in our sample. And then we want the mean of these values. The command that Excel uses for that is average, or the function that they use. So they say type equals average, open parentheses, and then you want to select those 11 cells again, close parentheses. And then you want the sample standard deviation. So the command here is stdev, and you see the one that says .s, that's for sample. So we have stdev.s of, open parentheses, select these guys, close parentheses, and you get that. Okay, so now we've got our N1, X1 bar, and X2 bar. We need our N2, X2 bar, and S2. And that was actually given to us in that summary page on MyLab Statistics. So let's go over there and see what it says. Okay, so we just computed N sub 1, X sub 1 bar, and X sub 2 bar. And then we've got the high lead level summary statistics over here. So it looks like we had 11 IQ scores. The mean IQ score for that high lead level group, the mean of those 11 scores was 89.097. It's below average. And the standard deviation for that high lead level group was 10.977. So we're going to type all of this into our Excel spreadsheet so that we can use it to do our computation or other calculations. So I'm just typing now. I've got 11, 89.097, and S2 equals 10.977. I just had that written on my scratch paper over there. Now, to compute our test statistic T, let me just remind you what that formula looks like. We need X sub 1 bar minus X sub 2 bar for the numerator. We need this to be our A and this to be our B, and we want the square root of A plus B for our denominator, and then we'll take that difference, or excuse me, that quotient of that value over that value. So that's the plan. Let's do that in Excel now. Okay, so we want X sub 1 bar minus X sub 2 bar, and here's X sub 1 bar. We're subtracting X sub 2 bar. So we get about 0.36. So it's not a very different, there's not much of a difference, not even a full IQ point between the two groups. Okay. And then we need A and B. A is equal to that first sample standard deviation squared, or if you want, you can call that the sample variance for the first sample. And then we're dividing by the sample size. Now that's just me writing it down so that I remember what A represents. You don't have to type that in, but sometimes it's helpful to leave notes for yourself or leave notes for other people if you're sharing your spreadsheets with them. If you walk away and you've given them some spreadsheet, it's nice for them to know what exactly Excel is calculating. So we're going to open parentheses, and the open parentheses again for the numerator. I want that sample standard deviation squared, or sample variance if you prefer, divided by the sample size, close parentheses. B looks just like that, but instead of using the sample statistics for the first group, we're going to use the sample statistics for the second group. So we'll take this standard deviation, we'll square it. Oops, I'll open parentheses for that. And then we'll divide by the sample size, close parentheses, and we get that. And then the denominator for our test statistic T, that's an estimated standard deviation of the distribution of X sub 1 bar minus X sub 2 bar. That is the square root of A plus B. So use the function sqrt in Excel, open parentheses, type A plus B, or you're just selecting A and B as cells and then closing the parentheses. And then you've got your estimated standard deviation there. And then our test statistic T has that X sub 1 bar minus X sub 2 bar in the numerator, and then you're subtracting the difference between the population means, which we're assuming to be 0 because we're assuming that the null hypothesis is true, And then we're dividing by this estimate for the standard deviation of that distribution of x sub 1 bar minus x sub 2 bar. And so we get this. It's really not that extreme, is it? So our x sub 1 bar minus x sub 2 bar was approximately let me highlight this for you there, 0.36. So it's not even half of an IQ point of a difference between the two groups. And then the corresponding test statistic T is also very small. It's 0.076 approximately. I want to share my paper with you again so that you can see how I'm visualizing this for myself. Okay, so we're saying to ourselves, if this x sub 1 bar minus x sub 2 bar is equal to this value, and the distribution should have the same shape. I didn't do a very good job in drawing it. The corresponding T value is this one. We're saying to ourselves, is this test statistic T significantly high given that the null hypothesis is true, which is the same as asking, is x sub 1 bar minus x sub 2 bar significantly high given that the null hypothesis is true? In order to determine whether it's significantly high or low, we're going to use the corresponding p-value. You could also use critical values of T and compare to that as well. But I think we're going to use the p-value this time. That's what MyLab Statistics tends to do. So let's check it out in the homework. Let's see what they're asking us next. Okay, so our test statistic rounded to 2 decimal places was just 0.08. Tiny. Okay. And then it asks for the p-value, and they ask us to round to 3 decimal places as needed. In order to compute the p-value, we're going to need the appropriate number of degrees of freedom. I'm going to do that in Excel as well. Now, if I want the exact number of degrees of freedom, I can use this formula. Got a plus b, and I'm squaring that. And then I'm dividing by a squared over the first sample size minus 1 plus b squared over the second sample size minus 1. That's going to give me the exact degrees of freedom. And this is featuring the numbers a and b, where a is that first sample standard deviation squared over n1, the sample size, and b is that second sample standard deviation squared over n2. Or you could just call those sample variances if you want. Once we have those, and we do have those in our Excel spreadsheet, it's pretty easy to compute this exact number of degrees of freedom. So that's one way of computing the degrees of freedom. That's what I would recommend if you can compute it that way. Now, if we are just using, let's say, table A3 to come up with critical values, and we don't have access to all of this technology that would help us do this computation, then we can make a conservative estimate of the degrees of freedom. And that is given by the minimum of the first sample size minus 1 and the second sample size minus 1. So in our case, the first sample size was 11. So 11 minus 1 is going to be 10. And the second sample size also happened to be 11. So obviously the minimum of 10 and 10 is 10. So we can compute our p-value using this as our number of degrees of freedom, or using the number of degrees of freedom given by this. This is more accurate, so I prefer to use this when I can. And since we're finding a p-value, we're going to have to use technology anyway. So I think I would rather use technology to get an exact answer for the degrees of freedom rather than using this conservative estimate. What I think we'll do in this video, though, is show you how we can use both of these to get different p-values, and you'll see how similar the p-values are, even though the degrees of freedom might be very different. So let's go to Excel and compute the exact degrees of freedom, and then use this number of degrees of freedom and this number of degrees of freedom to get the corresponding p-values, and then we'll see how similar they are. Okay, for my exact degrees of freedom, I'm going to do the numerator and denominator separately. The numerator is a plus b squared. So I'll type equals, open parentheses, there's my a, and there's my b, and I want to square them. Square the sum of those. And the denominator is a squared over the sample size minus 1. So I have a squared in parentheses divided by, open parentheses for the denominator, the corresponding sample size minus 1. And then we're adding that second fraction. And I want b squared over here. Here's my b. I want to square it. And then I want to divide by that sample size n sub 2 minus 1. I get the denominator. So the exact number of degrees of freedom is that numerator, divided by the denominator. And we get about 20 degrees of freedom, which is quite a bit more than that 10 degrees of freedom in our conservative estimate. So let's find p-values using the exact number of degrees of freedom and with the conservative estimate of the number of degrees of freedom. I don't know why it's automatically capitalizing that. I'm going to keep trying to get it to stop. There we go. Okay, so if I want the p-value, that means I want an area associated with a particular test statistic. So I'm going to type t dot dist. Ooh, actually, we need to think about whether we're doing area to the left or the right. I forgot to talk about that. So I'll share my paper with you again. Okay, so we're over here. And in order to decide what my p-value is, I need to think about whether I have a left-tailed test, a right-tailed test, or a two-tailed test. And that is determined by the alternative hypothesis. Since our alternative hypothesis features a greater than sign, you can think of that as an arrow pointing to the right. This is going to be a right-tailed test. So the p-value is the probability of getting a test statistic as large as ours or more or greater than ours, more extreme than ours. And we're going more extreme to the right because it's a right-tailed test. So this is our p-value, that area. And that's the same as the probability of getting an x sub 1 bar minus x sub 2 bar as extreme as ours or more extreme than ours. So that's the p-value. That's what we want. So we want the area to the right of this test statistic. So when I use Excel to compute my p-values now, that's a probability that our test statistic is equal to the value that we got or greater than that value. The function that we use in Excel for this is t.dist.rt for right tail. And then we will enter our test statistic here. And then we'll enter the appropriate number of degrees of freedom. And then I believe, well, I don't think it asks for anything after that. When you tell it right tail, then that's good enough. So this is t sub test, and this is the number of degrees of freedom. Okay, so you've actually got two options. You can either use this number of degrees of freedom, the exact value, which we saw in our spreadsheet was close to 20. I think it was like 19.99 or something like that. This is going to be a better p-value. It's a more accurate p-value. Or you can use that rough estimate that comes from this more conservative number of degrees of freedom. So we would enter the test statistic here. We'd say we've got 10 degrees of freedom, and that's going to give us a different p-value. So that's where df, our degrees of freedom, is given by the minimum of that first sample size minus 1 and the second sample size minus 1. Okay, let's go to Excel and actually compute this. Okay, so I'm typing t.dist.rt for right tail, and I want my t-value, which is right here, and the exact number of degrees of freedom, which are right there. So I got a p-value of approximately 0.47. So that's the probability of getting a test statistic as extreme as ours or more extreme is 0.47, or there's a 47% chance of getting a test statistic as extreme as ours or more than that, given that the null hypothesis is true. So this is very likely to occur due to chance. Now, if we want to use the conservative estimate given by that minimum of the two sample sizes, one less than each of the two sample sizes, we type equals t dot dist dot rt open parentheses, and we'll enter the test statistic again, and then we'll use that minimum of those two sample sizes, which was 10. See how similar they are? The exact p-value is 0.4700, and the p-value with the conservative estimate of the number of degrees of freedom, is 0.4703. So the difference between them is about 0.0003. That's usually not that important, especially when we're estimating our p-value or we're rounding our p-value to 3 decimal places. We're not even going to see that 4th decimal place. The only thing it could potentially change is that 3rd decimal place, which typically won't make or break our decision about alpha and our comparison from p to alpha, or comparison between p and alpha. So we've got these two p-values. I bet they're both more than alpha, so I think we're going to fail to reject the null. But let's enter these in MyLab statistics. Okay, rounding to 3 decimal places, both answers are the same. We have 0.470 in that case. Great, and then we are going to state our conclusion for the test. Okay, so our test involved a 0.01 significance level, so that's our alpha. And we're going to compare our p-value of 0.47 to alpha. In either case, p is greater than alpha, so we are going to fail to reject the null. Oops, fail to reject the null. So what we're saying here is the value of our test statistic is very likely to occur due to chance, given that our null hypothesis is true. That means the same thing about our x sub 1 bar minus x sub 2 bar. So that particular value of x sub 1 bar minus x sub 2 bar that we obtained from our sample is likely to occur due to chance, given that the null hypothesis is true. So we can't say that we accept the null hypothesis. We haven't proven that the null is true, but we can say that we don't have enough evidence to reject the null. We don't have enough evidence to say that the null hypothesis is not true. Evidence suggests that the null hypothesis might be true. Okay, so now we are failing to reject the null, but we need to decide what to say about the original claim. That requires that we look at the original claim and how it compares to the null hypothesis. So we go over here and we see that our claim was the alternative hypothesis. So when we fail to reject the null, we're saying that this might be true. And if we're saying that this might be true, it looks like we don't have enough evidence to support our claim. So we'll say this: there is not sufficient evidence to support the claim that ... whatever the claim was. So there's not sufficient evidence to support the claim that mean IQ scores for subjects with medium lead levels, or the mean IQ score for subjects with medium lead levels is higher than the mean for subjects with high lead levels. We don't have enough evidence to support that, at least not with these two samples that only had 11 subjects each in them. So let's go back to my lab statistics and enter that there. So we are failing to reject the null hypothesis. And we're saying there's not sufficient evidence to support the claim. Okay, great. And then the next part asks us to construct a confidence interval suitable for testing the claim that mean IQ scores for subjects with medium lead levels is higher than the mean for subjects with high lead levels. Okay, I'll share my paper with you again. So in order to construct an appropriate confidence interval, we need to know how much area is in the tails. And the area in the tails always relates to that significance level of our hypothesis test, but it doesn't always relate in the same way. It relates in different ways if you have a two-tailed test as opposed to a single-tailed test, a left-tailed test or a right-tailed test. So I looked up my alpha. My alpha is 0.01. That's what we were requested to, that was what our requested significance level in the problem statement. And then in order to decide whether it was a right-tailed test or a left-tailed test, I look at my alternative hypothesis. Since I've got a greater than sign, I can think of that as an arrow pointing to the right. So this is a right-tailed test. So when we construct our confidence interval, when we find the corresponding critical values of t, this is typically denoted t sub alpha over 2. The area that we want in that top right tail is actually alpha this time. It's not alpha over 2, it's alpha. And it should be more symmetric than that. Sorry about that picture. But we've got an alpha area in the top right tail. And because a confidence interval is always two-tailed, I want the same area in the left tail. So if I've got 1% of the area here and 1% here, I must have 98% of the area in the middle. So our critical value of t is not t sub alpha over 2 this time, it's t sub 0.01. That actually ends up being t sub alpha because it's a right-tailed test. In order to find this critical value of t, I need to find the t-score that has the area to the left of 0.98 plus 0.01. So I need the area to the left to be 0.99. In order to find that, I'm going to use my inverse function for t. In Excel, that's t dot inverse. And then you typically have to give the probability that you're interested in. So that's the area to the left of 0.99, and then the number of degrees of freedom. And we can either use the exact degrees of freedom, which was about 19.99, or we can use that conservative estimate of our number of degrees of freedom, which was the minimum of n sub 1 minus 1 and n sub 2 minus 1, which was 10. And we'll get two different values for that test statistic t. Now, remember, we're constructing a confidence interval, and the confidence interval looks like this. We want to know what is the range of values that mu sub 1 minus mu sub 2 may take on. What is a confidence interval estimate for this difference between these two population means? Well, in order to find those, we need a point estimate of mu sub 1 minus mu sub 2. That's given by x sub 1 bar minus x sub 2 bar. And then we're going to add and subtract our margin of error. So I'm taking that x sub 1 bar minus x sub 2 bar in both cases. And here I'm subtracting the error. And here I'm adding the error. This is my lower limit, for my confidence interval, and this is my upper limit for my confidence interval. And the error is given by this formula. Actually, let me write this down. X sub 1 bar minus x sub 2 bar. That's actually already on our spreadsheet. We calculated that. That was about 0.3575. The error is given by t sub alpha over 2 typically. But in this case, for our confidence interval that is appropriate for this hypothesis test, we're using t sub 0.01 times the appropriate estimated standard deviation, which is this. And actually, that's already on our spreadsheet. So all we really needed, we already had this and we already have this, was the value of t sub 0.01, which we can find using one of these formulas. And then we will multiply that by our estimated standard deviation. That together will give us the margin of error. Then we'll take that margin of error and add it and subtract it from this value to get the upper and lower confidence confidence interval limits that go right here and here. And typically, I believe MyLab Statistics likes us to round those values to 3 decimal places. So we'll make sure to do that as well. So let's do all of that in Excel now. Okay, so I want my t sub 0.01. And I can do that with the exact number of degrees of freedom, and I can compute that with the conservative estimate of the number of degrees of freedom. So we'll type equals t dot inv, open parentheses, the probability, that's the area to the left, is 0.99, and the number of degrees of freedom can be given by this exact value. Or we can do t dot inv, and we still want that probability of 0.99, and we could use the estimated degrees of freedom that is given by the minimum of 1 less than each sample size. We've got 2 values, and then you pick the minimum. And actually, that's a big difference in that t sub 0.01. Okay, now we're going to get 2 margins of error that depend on these guys. So one margin of error can be computed with the exact number of degrees of freedom. I think I'm just going to denote it by capital E because it'll make it easier. And then we'll use the conservative estimate to get a value, the conservative estimate of the number of degrees of freedom, to get a value for the margin of error as well. So we'll take t sub 0.01 and we'll multiply by that estimated standard deviation, which we computed earlier. And here we'll do the same thing, t sub 0.01 from the conservative estimate of the number of degrees of freedom, and we multiply that by the standard deviation again. Okay, and then for each of these, we can compute upper and lower limits for our confidence intervals. So I will do that twice, here one with the exact degrees of freedom, and then the other one with the conservative estimate of the number of degrees of freedom. And I'm just typing upper and lower limit for me to remind myself what I'm asking it to compute. So the upper limit takes x sub 1 bar minus x sub 2 bar, and it adds the error. And here I'm using the exact number of degrees of freedom. And then we have x sub 1 bar minus x sub 2 bar, and then we're subtracting the error. So we've got these values, and if we round to 3 decimal places, we get that and that. Okay, with a conservative estimate of the number of degrees of freedom, let's do the same thing. We'll use x sub 1 bar minus x sub 2 bar, and then we add the error, but let's use the second margin of error. And then we're going to take x sub 1 bar minus x sub 2 bar and subtract the error. Those are quite a bit different this time. It's because those margins of error are very different. And the margins of error are very different because the t sub 0.01 is very different depending on the number of degrees of freedom. G20, did I give it the right one? Yes, I did. Okay. So let's use the exact number of degrees of freedom. In that case, our lower limit is negative 11.553, and our upper limit is positive 12.268, rounded to 3 decimal places. Let's see if MyLab Statistics likes that. It's probably going to like that better than this conservative estimate, but it should give you, MyLab Statistics, excuse me, should accept both answers, because we know that students are using different resources to answer these questions. Okay, so my lower limit is negative 11.553, and my upper limit is 12.268. Oops. Okay. That's what I did, I thought. Okay, it's giving me the same advice that I followed over there, but I guess it didn't like the answer that I got with the exact number of degrees of freedom. So let's type in the other answer instead. So these are the answers that we got using our conservative estimate of the number of degrees of freedom. So I have negative 12.605 and 13.320. Let's see if it likes those. Hopefully it does. Unless I made a mistake somewhere else. It's very possible. Okay, so then using the more conservative estimate, my lower limit for the confidence interval is negative 12.605, and my upper limit is 13.320. I must have done something wrong. Okay. Let's go back to my paper and see what the problem is. Okay, I've got a 0.01 significance level, got a right-tailed test. So my alpha is 0.01. So I've got alpha area in this tail, alpha area in this tail. So T sub 0.01 is given by this. Okay. We had two different values of that. And then we take each of those and we multiply by the estimated standard deviation. And then we add and subtract that x sub 1 bar minus x sub 2 bar, or take this and add and subtract the margin of error from each of those. I just don't see a mistake here. It liked my p-values, and my p-values were computed with the exact number of degrees of freedom, and also with this minimum of n sub 1 minus 1 and n sub 2 minus 1. I just don't see the mistake. Let's go to Excel and try to find it. I just realized what I did. It's so silly. I didn't read the fine print. It asks us to round to 2 decimal places as needed, and I had rounded to 3. So that should be a 1, and that should be a 0.32. That's silly. What a silly mistake. I know you guys relate to that. So many of my students call me and they say, or they email me or text me and say, oh my goodness, I'm getting the wrong answer. We didn't look at the fine print. Round to 2 decimal places, not 3. Well, it's encouraging to know that the mistake was not in the mathematics, but it was in reading the fine print asking us to round to 2 decimal places. It happens. You see, it happens to me too. It's okay. Then the question says, does the confidence interval support the conclusion of the test? The conclusion of the test was to fail to reject the null hypothesis. Remember, that means that the null hypothesis might be true, and mu sub 1 minus mu sub 2 equals 0 is in that interval. So that's saying that the null hypothesis might be true. So yes, the confidence interval does support the conclusion of the test because the confidence interval contains 0. All right, that's how we solved that problem. Thank you for understanding on that little part at the end. I hate when that happens. Just make sure you read the little print in blue, because sometimes they change it on you. Sometimes they want you to round to 2 decimal places. Sometimes they want you to round to 3 decimal places, and you really have to look at it and read it to make sure that you get the right answer.